I found that off-the-shelf enclosures were too small for this Lulzbot printer, so I designed my own using a frame made out of 1010 extruded aluminum. When I put together the bill of materials, I noticed that the connecting hardware, like these corner brackets, added up to be more expensive than the extrusions. While they are metal, which is great for holding weight, they probably could have been 3D printed, which is exactly what I did for the brackets that hold the panels. But how do I know how much weight these brackets can actually hold? Mechanical engineers often spend a lot of time analyzing and solving complex equations to figure out how forces put stress on objects or assemblies. Probably the most popular way to calculate stress and deformation is by using the Finite Element Method, or FEM. 2D or 3D objects are broken down into simple shapes, often triangles, to create a mesh. These are the finite elements that make the equations work. From there, stresses, heat transfer, fluid flow, or electromagnetic potential can be estimated over that body. Using the finite element method to analyze these processes is known as Finite Element Analysis, or FEA. For example, engineers use FEM to predict how this car would deform during a crash. I'm not a mechanical engineer, and I haven't studied statics, so I couldn't perform FEA by hand right now. But FreeCAD comes equipped with an FEM Workbench that can estimate the deformation and stress on my bracket design. It can handle multiple solids, electromagnetics, and fluid calculations. But to start, we'll perform static analysis to figure out how a single bracket behaves under a light load. Let's get started. Up until now, we've looked at designing parts and assemblies. In this final episode, we'll look at how to use FreeCAD to analyze those mechanical designs for potential failure points. In FreeCAD, make sure you're in the Part Design Workbench, create a new document, create a new body, and we want to change the units to imperial. Sorry, 1010 is going to be using inches. So click on your document, go to Properties, go down to Unit System, and change that to US Customary. Let's create a new sketch on the XY plane. We're going to create a square, right-click, create a circle inside of it, right-click that. Let's make this symmetrical around the origin, like so. Right-click to end. We're going to make this a square, so make the length and width equal. Let's set the distance to be 1 inch. That looks good. Right-click. And let's set the diameter of the circle to be 0.266 inches. This is a loose fit for a 1/4 bolt. Say OK. Right-click to end. Looks like we're fully constrained. Let's go ahead and pad this to 0.08 inches. That's about 2 millimeters, just what I'm used to. Let's create a sketch on this face. Let's bring in this part of the original pad as external geometry. We're going to create a square that goes down like that. Make sure that's connected, if not, at a concentric constraint to that point. Let's set the width and height to be equal. That's not constrained. So constrained concentric, let's put it there. 8 is redundant. Let's get rid of that. That looks good. Let's create a circle somewhere in the middle. Right click. Let's set the diameter to be 0.266 inches like we did before. Let's do symmetry between this point, and the center of the circle. Right click. There's a redundant constraint, number 11. So let's highlight that, delete it, and we should be fully constrained. Let's pad that, but we want to go inside. So let's make it 0.08 inches. Let's go reversed. So now we're inside, and this should be 1 inch, and that should be 1 inch. Click OK. And we have our very basic shape ready to perform FEM analysis. We'll analyze our part using the FEM Workbench. The FreeCAD Wiki has a great diagram showing the general workflow. We'll start by bringing in our solid made with the Part Design Workbench. From there, we'll use the FEM Workbench to assign a material to that solid, as well as define the constraints and loads. We'll use a third-party tool to turn the solid into a mesh and then run a solver to perform the actual finite element method. From there, we'll view the results. There's a lot going on in this workbench, but I'll show you the basics to get started. Just for fun, let's go back to the Document Properties pane, and we're going to change the unit system back to metric, or standard in this case. That's going to allow us to view the results from the solver in metric units, which I find a little easier to read, even though we created this using imperial units. That's fine. To start, let's go to the FEM Workbench. You'll notice that our tools change. We need to create a new analysis container, sort of like what we did for assembly. This is a container that we put everything under, including the body that we're analyzing, our results, the meshes, and so on. Everything just gets put under this container. Note that it's not linear. It's not a linear set of instructions like you would find in a part design body, but rather it's just a collection of stuff. You want to make sure it is active with this light purple here, so you can right-click Active Body, right-click Active Analysis, and make sure that is light purple. You'll notice that when you drop it down, it comes with a solver object. This is an external finite element method program integrated into FreeCAD. It comes with the FreeCAD installation. If you don't see this, you'll want to click this rainbow S over here to add a solver object. The third-party tool is the CalculiX or Calculix standard. This is an open source finite element solver, and like I mentioned, it comes bundled with FreeCAD in this case. Next, we want to click the Material for Solid button. This is going to assign a material. We can select the different types of materials here. So I'm going to scroll until I find PLA generic, since that's what I'm 3D printing this out of. Feel free to use some other material. I find that this editor is not working for me. If I click it, yeah, you get a problem here. Hopefully that'll be fixed in a future version. But I can edit the materials here. Notice that the materials are set for PLA, but I'm able to set them here if I need to for another type of material. We'll leave them at their defaults for now. You can add specific geometry, so you can click to add here and you can select faces and edges, but if we leave it blank, it's just going to assume use everything. And I believe I can select solid, can click add, and it's going to add that. And for whatever weird reason, I can't delete things from this list. Oh, there we go. Right click, clear list. There it is. So I'm going to leave it blank, and that will pull in everything from the body up here. It will, in essence, assign a material to everything. Next, we want to add our constraints. So once we're happy with this material, click OK. The first constraint we want to add is our boundary condition, or a fixed constraint. So something that doesn't move. It has to stay relatively stable. So I'm going to think about adding a bolt through here to keep this part fixed, and then my load is going to be on the top here. You could also assign it to a face here. So if I want to assign it to a face, I'll click the face, I'll click the fixed boundary condition, or actually it doesn't assign it to that face right away. So I click add, then I click it to that face, and that keeps that face nice and solid for me. That's not what we want, so I'll cancel that. Let's bring back the fixed boundary condition. We'll click add, and we'll use the inside face here. Now that's like adding a bolt to here, so this face doesn't move, this inside circle. Click OK. Then we want to add our load, which is going to be another constraint. That's the load part up here. So we're going to use this tool, the force load. We're going to add, and we're going to click this top face like that. Notice that these arrows are pointing the wrong way for our load. So we actually want to reverse the direction so that they're pointing down. This should be in newtons, and I want this to hold, I don't know, like 5 kilograms. Earth's gravity is about 9.8 meters per second, with force equals mass times acceleration. We have 5 kilograms times 9.8 meters per second squared. It comes out to be about 49. Let's just round this up to 50 newtons. So we'll say OK. Next, we need to create a mesh. This is used for the actual calculations for the finite elements. It basically breaks down our solid into finite elements, like little triangles, and uses those points or faces to calculate numerically the forces acting on this object. It could be temperature, it could be a temperature gradient, it could be looking at deflection, how much stress, but that's where the idea of finite element analysis comes into play. You have two options for creating meshes. Both are external third-party programs. Both are open source and both come bundled with FreeCAD. The first is NetGen. This seems to be better maintained. The next is GMSH. This one doesn't seem to be as popular, and I couldn't really get it to work, so we're going to go with NetGen. If these buttons are grayed out, you need to click on the body that you want to create a mesh out of, and make sure your tip is set to the final part. Let's make this active. Let's say I set the tip to here. You're only going to get this top part, and that's not going to work so well. Make sure the tip is set to the part you want in your body. I'm going to deactivate this, but I'm going to make sure it's clicked. And it looks like it brought me back to part design. So let's go to FEM. Let's click on the body. Now these two options are no longer grayed out. Let's select FEM Mesh by NetGen. The max size is the maximum size of each mesh element. It should be in millimeters. Let's try 1 and click apply. You should get a lot of little small polygons here. Let's try 5, click apply there. Now we have some smaller ones, especially along the edges, and some larger ones. Going larger doesn't seem to change a whole lot. And note that the smaller the mesh elements, you get better accuracy or resolution, especially in these edges, but it's going to require more computation. So it's always a balancing act between how much computation you're willing to spend on FEM. The minimum size we'll leave at the default 0. We'll let NetGen figure it out. Second order determines where the calculations are performed. So if we uncheck that, that means use first order calculations, and the nodes used for the numerical calculations are just at the corners of the elements. So like at the points of this triangle. If we leave second order on, there are now nodes at the endpoints and nodes at the midpoints between the corners. Generally, second order is more accurate, especially for things like deformation and stress calculations. But once again, it's more computationally expensive. So if you're really bogging down your computer, maybe try unchecking that and you can still get a decent approximation. We'll leave it checked for now since this is a fairly simple part. The fineness dropdown determines how the mesh is calculated. Feel free to play around with this so you can see how the mesh changes. We'll leave it at moderate for now. Click apply, and we're back to where we were. Optimize is where NetGen tries to improve the mesh quality. We'll just leave this on. We'll click apply if not done already. And you can see the number of nodes, elements, and 3D elements in the mesh. As this number goes up, things can become more accurate, especially if you have a denser amount of elements for your model. But the more of these you have, the more computation is required. Click OK, and now we have a defined mesh. Let's double-click on the solver in the tree view, and that should bring up something in the task pane. We have several options for the kind of analysis to perform. We want static analysis. We're not looking at things like temperature gradients, and we don't care about, say, vibration right now. The trick is to write this INP file. This creates an input file with everything we've done up to this point. Feel free to click Edit to look at the file. It defines the mesh, the material, the boundary conditions, which includes our fixed and force constraints. Note that you need to regenerate this INP file every single time you make changes in your analysis setup or your mesh or your constraints. So if you're having trouble running the solver, don't forget to click this button. Let's go ahead and close our editor. Then we can run CalculiX. This will read in the INP file, which is the input. And this might take a minute or so. And what you want to do is scroll down on your output here and looking for something that says done without error. That means the solver was performed correctly. You should also see a color bar appear on the right side of the 3D view. Go ahead and click close. You can see that we've got the mesh and the body still here. So let's make sure the body is hidden. We'll make sure that the mesh is hidden, and we should end up with just our results. There are two ways to view the results. Both give similar data. They are separate objects in the tree view. The first is this CCX results, and the next is this pipeline CCX results. These are two separate results objects. Let's hide the pipeline one for now, and let's show the CCX results and drop it down and unhide the CCX results mesh. Click away to view that. It looks just like our mesh. You can double-click on CCX results to get something in the task pane. There are a few things you can view here. We want to look at the displacement magnitude. You can see the minimum to maximum displacement. These are shown in the colors here, with green being the minimum, red, this dark red color being the maximum. You can see it's going to deflect up to 3.5 millimeters, which is quite a lot for this. I kind of expect that to break under 5 kilograms. If you come down to this slider, you can click Show, and I'm going to change slider max. That's actually a factor. So if we slid this all the way up, you can see something bonkers happening here. That's actually saying, instead of 5 kilograms, that's saying, oh, what happens if you hold 500 kilograms? So let's change this to 1, since we estimated our maximum load to be about 5 kilograms on top of this thing. And now you can see how this deflects. That looks a little better with 5 kilograms. So up to 5 kilograms here, you can see it deflects about that much. That's not great for a plastic piece. I would kind of expect that to put a lot of stress and perhaps fracture. The other thing we can do is view the von Mises stress. This allows you to view the total amount of stress, assuming 5 kilograms on top of the bracket. Von Mises assumes a ductile material. That means the material, in this case our plastic, can bend or stretch before fracturing. Most metals and some plastics are considered ductile. PLA and PETG are generally considered somewhat ductile. They might have some inaccuracies, but that's okay. Things like acrylic is very brittle, so the von Mises stress calculations would not work here. Also note that we are assuming an isotropic material. This means that the properties are the same in all the directions and all the axes. 3D printing is not isotropic. The horizontal XY behaves differently than between the layers in the Z-axis. So take all these results with a grain of salt. These kind of assume this is made out of one piece of material, in this case PLA plastic, that's not been 3D printed. But it's a decent starting point for us to try to figure out how can we make this shape better. The green areas show the minimum stress, which is 11 kilopascals, and the red area is the maximum, which is around 64 megapascals. Notice that the displacement slider only shows the relative deflection and doesn't affect the stress calculation. Also note that when we're looking at stress, even though it looks like it's up here, these might not be super accurate because we don't have a lot of resolution around here. So take a lot of these numbers with a grain of salt, but it does demonstrate where the maximum stress. And you can check that with some common sense. If I put a load here, if the only attachment point is a bolt, then yeah, I should see a bunch of stress pile up right at the top of the bolt hole here. Go ahead and hide the CCX results mesh. And let's show the pipeline CCX results. Feel free to double-click that to get a task here. Leave the mode as surface. And we want to change the field to displacement magnitude. The color bars are in meters, and just like we saw with the other results object, the maximum displacement will happen on this edge here, and it will be about 3.5 millimeters. We can change the field to von Mises stress, and the color bar should be in pascals. And from this, we can see that the maximum stress is going to be something like 60 megapascals. Let's click OK because we're done with that. Feel free to hide that. And let's bring this back. Let's double click on the CCX results. In theory, that should line up with the 63 megapascals we saw here. With this in mind, let's hide our results for now. You can say bring one of these back. We'll close out of this. Now let's try to strengthen this object by adding some material to the side and see how that affects our results. We will hide our analysis container. Let's unhide our body, double click on it to make it the active body, or you can right click, say active body. And let's create a sketch on the side here. So I'm going to click one of these side faces. I'm going to click create sketch. I'm going to bring in these lines, these internal lines as external geometry. I'm going to create a triangle that follows these like so. Let's click there. Click here to create that line. Click here to create that line. Right click. This should be a fully constrained sketch. Click close. Let's pad this. We will reverse it so it goes inside, and we will make it 2 millimeters, or like we did earlier, about 0.08 inches, and that should calculate that for us. Notice we set the units here, and FreeCAD figures out how to convert those units to our document units, which is millimeters. So click OK. And if you click here, you can see the length given in millimeters instead. Now with the pad selected, let's mirror this. So we'll use the mirror tool. We will go about the YZ plane instead of flipping it like we did there. So let's do the YZ plane. Let's click OK. Now we will hide the body. We can right click, make that not the active body. Let's double click on an analysis to make it active and press space to show it. Notice that the mesh has been updated, but the results are not. We should see this mesh colored in here. So if I hide those, you can see the mesh there. And if I hide the mesh and bring the results back, it's still the old one. So we need to run the solver again. So let's hide the results. Double click on the solver. Remember before we updated something here, so write INP file. And if you ever see this grayed out like this, that means you need to write that INP file again. Run the solver and wait a moment while that finishes. Now we want to show the results again. So scroll down here. Let's show the mesh under CCX results. So show that. There we go. That mesh has been updated. That looks really good. You can double click on CCX results. Active task dialog open. Thank you for the reminder. Let's close that. Now we can double click on that. We will view the displacement magnitude, and you can see this is much less than before. So we can show it bends less than 0.5 millimeter, which is a lot less than before. So now I feel a lot more confident that this is going to be able to support 5 kilograms. Similarly, we can view the von Mises stress, and that is less than half of the 63 megapascals we had earlier. That's around that bolt there. Let's close out of this. Let's double click on the pipeline results and press space to show it. If we go field, show displacement magnitude. Let's keep it at surface. Once again, we still have a problem up here, or rather this is where the max displacement will be. Whether or not it's a problem depends on the material. And you can see it's going to be displaced by about 0.5 millimeter. We can view the von Mises stress, and that bolt hole is going to see what's predicted to be about 27 megapascals around that bolt hole. The British statistician George E.P. Box is often attributed for the quote, "All models are wrong, but some are useful." This applies to finite element analysis as well as statistical models. In other words, take all of this with a grain of salt and try to take a holistic view of your design. Due to the discretizing of the part into mesh components and numerical estimations, the stress numbers won't be exact. Stress patterns and how much general deflection happens are often more useful than figuring out precise numerical values. If you are designing important mechanical components, like for aircraft, then you'll want to dive deeper into stress analysis and use something like the Mill Handbook 5 to see what loads various materials can handle. I won't get into this here though. I don't have a particular challenge for you, but maybe just play around with the FEM Workbench. See if you can reduce the displacement and stress even more by, say, making the bracket wider or longer to accommodate another mounting hole. If you've made it this far, I want to say, well done. You've hit the limit of my FreeCAD knowledge. There is plenty that I did not cover, but by now, you should have the basic building blocks needed to start designing your own mechanical contraptions. If you need additional help, there are a few resources that I recommend. The FreeCAD Wiki is a great reference for all the different workbenches and tools you'll find in the program. Mango Jelly posts regular videos on his YouTube channel that I highly recommend checking out if you want to increase your skills even further. That's how I first started learning FreeCAD. And if you run into trouble, the FreeCAD forum is full of incredibly helpful individuals. I recommend searching there and starting a new thread if you can't find what you're looking for. Thank you for sticking it out until the end. I hope this series has helped you become comfortable working in FreeCAD. If you make something cool in FreeCAD and want to share it on X, Instagram, or LinkedIn, please tag DigiKey and add the hashtag DKFreeCAD. Good luck and happy hacking!